Welcome back to Physics 272. Last time, here's what we did. We reviewed electric potential, and we looked at the potential at one point in space. We said for configurations of charges that are made up of individual point charges, then in those cases, the electric field goes all the way to 0 at infinity. And so that gave us a reason to set the potential at infinity to 0. And in those cases, then, we were able to define the potential at any point in space relative to infinite separation, which we defined as 0. We discussed the potential inside of a conductor. Tell me what happens to a potential inside of a conductor. We use the fact that inside of a conducting material, inside of a metal, the electric field is 0 in equilibrium. So what did that tell us about the potential inside of a conductor in equilibrium? Okay, the potential doesn't change inside of a conductor in equilibrium. The potential is constant. So if we use that height analogy again, and we think of potential like height, so think of yourself walking around a landscape, and when you get to a region that's inside of a conductor, there's no slope. Okay, the electric field goes to 0, which means the slope of the thing is flat. So it's all flat, which means that as you walk from one spot to another inside the conductor, your height doesn't change. So that's what a conductor looks like in that landscape analogy. It's a plane. Okay, it's totally flat. So the potential, whatever it is, could be 5 volts. It's just constant inside there. The potential inside of an insulator we saw was more complicated, and the reason is that an insulator is more complicated, okay? An insulator is made up of little dipoles that sit where they are, but then when you apply an electric field, the dipoles can orient, okay? The dipoles can get a particular orientation to them. So we said that that was complicated inside the material, but we did an end run around the problem. We said, look, to try to figure out the electric field inside that complicated material is too much work, and anyway, we can't even measure inside the material and check ourselves. So let's do an end run around the problem where we said, let's look outside of the insulator, and if we tracked the electric field outside of the insulator, that gave us a way to integrate the electric field outside and find the voltage drop outside the insulator. And because of the height analogy, we knew that whatever the height difference was going around the insulator, that must be how high on average we have to climb inside the insulator. So we used that kind of an in-run way to solve the problem that way. So that's what the potential looked like inside of an insulator. And today we're going to get to the energy stored inside of a field, and then draw a line, an imaginary line right here. After that, we get into magnetic field. And magnetic field is chapter 18 material. So we'll talk about sources of magnetic field, and we'll talk about how a magnetic field is due to moving charges. And then we'll talk about cross products. First, we'll learn the right-hand rule in a physical way, which means use your right hand to figure it out. And then, if we have time today, I'll show you the math. Okay? So first, let's hit the energy density of an electric field. So an electric field has an energy associated just with its existence. So you're used to this idea that if I have a particle in space, right? So put a particle somewhere. It's got a particular mass associated with it, and it's got a particular energy associated with that particle's existence, right? E equals mc squared. The electric field, in the same way, by analogy, the electric field is a real physical object. And anytime there's a real physical object, it has an energy associated with its existence. So you're not used to visualizing a lot of the electric fields we discuss in class, but you do have senses that can detect electric fields. Your eyes, when your eyes detect light, that's a type of electric field, right? And you know, there are animals in the sea, all sorts of different animals that have kind of interesting ways to detect local electric field disturbances. And some of them even put out electric fields. So it's a real physical object, the electric field, and it's something then that just due to its existence in space, it has an energy associated with it. So we'll calculate that today, and I'll give you one way. Here's one way to calculate it. There are others, but here's one way to look at it. So let's start with a capacitor. I want to have a positively charged plate on the left and a negatively charged plate on the right. So given this setup, a capacitor with charge plus and minus Q, given a distance s between the plates, here are the equations I'm going to use to solve it. But let me tell you the physical setup first, and then we'll go back through which equations we need. I want to do the following. I want to hold the blue plate fixed, so it's not going to move. It's immovable. The red plate, though, which is a certain distance away, which has the positive charge on it, I'm going to let that guy move. What's it going to do when I let it go? Which way does the red plate's positively charged. Which way does the red plate want to move when I let it go? Yeah, it's going to move over and crash into the blue plate, okay? So it's going to crash in, and what we're going to think in these terms. When I let the red plate go, it started moving and it crashed. So some kind of energy was already there that was in the field itself. The field energy was already present. When I let the plate go, that gets converted into kinetic energy of the crash, okay? So what we want to do is find how much work the blue plate does on the red plate during this process, and that'll be equivalent to the energy that was already stored in the field. We're going to convert the energy in the field into work during the motion. So here's the equations I need. To do work, to calculate work, I need integral f dot dr. Okay? Well, what's the force on the red plate? The force on the red plate is its charge times the electric field it feels. So I need that equation. What's the electric field it feels? Well, I know what the electric field is in a capacitor. I'm going to write that down, and then we'll work out what electric field the red plate feels. But I do know that the electric field inside of a capacitor is sigma over epsilon naught, where sigma is charge per unit area on the plate. Okay? Do you have any questions so far? So far, it's just a setup. Okay? So the field, what I need to figure out what's the field that the red plate feels. Look at this equation here. This is the total electric field in the capacitor. How much of that is due to the blue plate? A half, okay? So there's a total electric field inside of here. Half of it is contributed by the red positively charged plate. Half of it is contributed by the blue negatively charged plate. If I want to think about the electric field that the red plate is experiencing, what's the force it's going to feel? It feels the electric field due to the blue plate. So that's the thing that I need. So I write that down. That's the field just due to the blue plate is half of the capacitor field. Okay? Then I'm going to calculate the work that the blue plate does on the red plate during this motion. So that's integral f dot dr. The force is QE. So I need the charge on the plate. So Q is the charge on the red plate. I need the electric field that the red plate feels, and that's this sigma over 2 epsilon naught. And then I need the direction of the force dotted into the direction of the motion. So in this case, the way I have it set up, I have the positive plate on the left. The positive plate is on, yeah, it is. That's your left. Okay, the positive plate is on your left. The negative plate is on your right. Which way is the positive plate going to move during this motion? So the positive plate moves along the x-axis. Okay? Which way is the force on the plate pointing? Same direction. That's why it's moving that direction, right? So the direction of the force and the direction of the motion are parallel. So that gives me this x hat dot dx. It just gives me a factor of 1, right? So now I integrate q sigma over 2 epsilon naught. And the integral dx is going to go from 0 to s. It's just got to cover that distance. So q, sigma, and 2 over epsilon naught, those are all constant. They come out of the integral. And then I have integral dx from 0 to s. Now over here, I'm just going to gather terms. This integral here gave me an s. So there's the s over all. Sigma, I've changed into q over a. So there's an extra power of q here, and there's the divided by a. Okay? Do you have any questions so far? All I did was calculate the work done on the red plate by the blue plate. Why is it 2 epsilon naught? Right here? Yeah, OK. So the factor of 2 here comes from what the red plate is experiencing as a field due to the blue plate. So I had to separate out the contribution of to the electric field from the blue plate only. So inside the capacitor, there's a total field, sigma over epsilon naught. But half that field is contributed by the red plate, and half is contributed by the blue plate. And as we know, charges don't move in response to their own electric fields. The charge will just move in response to external electric fields. So in this case, yeah. So thank you for asking. That's an important point. Okay? So that gives us then that the red plate's going to move in response to the field put out by the blue plate. Good question. Any other questions here? More comments? OK? All right. Now I'm just going to multiply by 1, because I'd like to rearrange this a little bit. Why am I going to bother rearranging an answer I already got? The question we really want to answer is, how much energy was in the electric field itself, right? Just due to the electric field existing, how much energy does that entail? What's the energy that was stored in the capacitor originally? And we just converted all that energy into work and then finally into kinetic energy of motion, okay? And so that initial energy I want to express in terms of the total field that was there. So now I'm going to rewrite it in terms of total field. So I'll multiply by some factors of 1 here. I'll multiply and divide by A, the area of the plates. I'll multiply and divide by epsilon naught. Why am I doing that? I want to find an electric field in here. And the electric field, the original total, now I'm going to work in terms of the total field because I want to know the energy that was in that capacitor, and there was a total field in there. So the total field is sigma over epsilon naught, which is Q over epsilon naught A. So I'm looking here for factors of Q over epsilon naught A. So I have two factors of Q, right? Q times Q, and I have an epsilon naught and an A. If I had another factor of epsilon naught A down there, I'd have 2 factors of the electric field. So I'll multiply, divide by A, multiply, divide by epsilon naught, and then all together I'll have a Q squared over epsilon naught squared over A squared. Gives me this E squared. That's the total electric field in the capacitor originally. Okay, and what's left over is a half. There's an epsilon naught up here and an area up here. Do you have any questions about how I got the electric field into there? Well, this is now the total electric field in the capacitor. Okay, all right, tell me about this, SA. One of the factors I have in here is SA. That's the distance between the plates and the capacitor times the area of the plates. What's the physical interpretation of S times A in this geometry? What is it? Volume, yeah. So that's the, right here I have sitting here the volume of the capacitor. All right? So let's keep that in mind. So here I've written up here again that the total energy that was originally in this system is a half epsilon naught E squared SA, where this SA you told me is a volume. So if this is equivalent to the energy that was originally stored in the capacitor, right? And then we let the red plate go, that energy got converted into work, which eventually got converted into kinetic energy, but the total energy is the same, right? So there's this volume sitting here. What I can think in terms of is, in the electric field itself, what's the energy per unit volume of the electric field? So what I'm doing here is I'm taking the original energy stored in the capacitor, which is equal to this work term. They're the same. Okay? And then dividing out the volume, where volume was SA. That gives me this equation. I'm left over with a half epsilon naught E total squared, and that's the energy per unit volume just due to an electric field existing. Do you have any questions about that? Okay, so the physical interpretation of this equation is that anywhere in space that I have an electric field, could be due to anything, I could look in a little volume, so look in a little volume, and there's electric field in that volume. So I take that electric field, right, put it in this equation, and that tells me the energy in that volume, right? So energy per unit volume is this equation here, a half epsilon naught E total squared. Do you have any questions or comments about that? All right, later when we talk about magnetic fields, we will have a similar equation for magnetic fields. It turns out that magnetic fields also store energy. They're an energy storage device, right? A magnet is an energy storage device. And so there's a particular energy associated with magnetic field. It'll look very similar. It'll also have a B squared in it, B, where B stands for the magnetic field. Okay. Any questions so far? All right. That was the end of chapter 17 lecture material. Now we're moving on to chapter 18, and chapter 18 is all about the magnetic field. Here is the list of key ideas that your textbook says for chapter 18. So the key ideas are that moving charged particles make a magnetic field, and that magnetic field is different from an electric field. The needle of a magnetic compass aligns with the direction of the net magnetic field, or the total magnetic field at its location. That's what a compass is for. It tells you, well, we use it to find north, but in fact, it'll always be pointing in the direction of the total magnetic field at its point in space. A current, we'll define what current is. It's a continuous flow of charge. And we'll see later later on in the chapter that we can use the superposition principle to calculate the total magnetic field at any point in space. So what happens when a compass is by itself? So we actually have a compass up here on this good old school technology of an overhead projector. Okay? So I have right here a compass on a frictionless point. And then when it comes to equilibrium, it's oriented in a particular direction. And its job, of course, is to point towards north. That's why people invented compasses. All right? Now, so when the compass is by itself and when it's in equilibrium, it's doing its thing. It feels the Earth's magnetic field strength, and it points in that direction. Now, what do you think is going to happen if I bring a magnet nearby? I have a magnet. What do you predict will happen if I put the magnet close to the compass? Yeah, it's going to affect it, right? OK, so this magnet coming in, it's already feeling it. OK. So compasses get messed up by, yeah, it's fun to see if you can get the thing to kick around. There you go. All right, so compasses get affected by a magnetic field in its vicinity. All right, so that messed it up. Let's try also putting a current-carrying wire near it. So here I have a wire that is not carrying current at the moment, okay? There's really shouldn't be anything happening there. But let's turn on the current, all right? And then in this case, there is magnetic field coming out of the wire. And we can see what's the effect. Okay, I can actually orient the compass by twisting the wire. Okay, I'm turning the wire, and that's dragging the compass along. So there's something going on here that's allowing me to control the direction of the compass just by controlling the direction of the wire. Okay, and then if I turn the current off, then the interaction is gone. So when the current's there, there's an interaction. When the current's not there, it's off. All right, so in these cases, when the compass was isolated, it pointed to Earth's magnetic north pole. When we brought a magnet nearby, the needle deflected. And when we brought a current-carrying wire near the compass, the needle was deflected again. All right. Now, the compass needle and the magnetic field. So what the compass needle does is it responds to any magnetic field. It doesn't care about the source. Could be a magnetic field due to the Earth. It could be a magnetic field due to a permanent magnet. It could be a magnetic field due to current. Okay, all those things work. All right, and here's my daughter's personal favorite, a duck. My daughter thinks that is the funniest joke in the world, right? 3 ducks walk into a bar. She goes crazy. Okay, she's 1 year old, so her humor might be a little different from yours, but I threw the magnetic duck in for my daughter. All right, so it also responds to a magnetic duck. The key idea is that the needle of a compass aligns with the net magnetic field no matter what the source. It just feels the net magnetic field strength. So here's some fun facts about Earth's magnetic field. All right, the fun facts are just for fun. You're not going to be tested over the fun facts. But the Earth has a magnetic field due to there's a molten core which can carry current, and that current-carrying molten core produces a magnetic field. That magnetic field drives more current, and so it's this self-sustaining dynamo. And it produces a magnetic field strength, which is small but good enough to run a compass by and navigate. So it's about 20 microtesla. Okay? A typical neodymium magnet, so if you've played with those teeny tiny permanent magnets, the really strong ones, they're called rare earth magnets or neodymium magnets. Those have a field of about a Tesla. So the Earth's magnetic field strength is about 10 to the 5 times smaller, so about 100,000 times smaller than that. The Earth's magnetic field strength is tilted from the rotational axis, right? The rotational axis of the Earth defines true north. Magnetic north is 11 degrees off of that, and it just tells you that the rotation of the Earth is not completely aligned with those currents that are circulating inside of it. Throughout Earth's history, by the way, there have been sign reversals in the magnetic field. So if you look back, how do we know that? Well, we study rocks, that's how we know it, okay? So if you gather enough rocks from all over the planet, you can get rocks that solidified at different times in Earth's history, and you can see that the ones that are magnetic solidified in different directions. They were presumably affected by Earth's magnetic field orientation. So we can actually map out several sign reversals throughout Earth's history. And has anybody ever seen the aurora borealis? Who's seen the aurora borealis? Yeah? Okay. I'm actually originally from the South, and so I didn't see this thing until I was camping up in Minnesota as an adult. And I saw at night, what in the world is going on with your clouds? You know, they keep changing and they're kind of glowing. Is this like a radioactive area? What's going on? And somebody said, no, it's aurora borealis. Okay, I really knew it was the aurora borealis, but it looked weird. It was weird. Anyway, so it's very pretty, and it's due to Earth's magnetic field. So here's what happens. And again, this is fun facts. You don't need to know this, but it's fun. So the sun is a big nuclear furnace. Right? If you know they might be giants, you've got a song stuck in your head now. But anyway, the sun is a gigantic nuclear furnace. Anyway, it's putting stuff out, puts out a lot of light, it puts out a lot of heat, and it also shoots out particles. It shoots out charged particles. When those particles get near the Earth, they get trapped on our magnetic field lines. So we have a bunch of magnetic field lines coming out of magnetic north and wrapping around. When a charged particle comes by, it gets trapped on it and spirals along the field line, and then those field lines funnel it into the North Pole or funnel it into the South Pole. And so if you can imagine all these charged particles coming crashing into your atmosphere, that's a lot of energy. And all that kinetic energy gets converted into the light of the aurora borealis. So that's kind of fun. And you know, if you're into chemistry, you can predict what the colors should be then of the aurora borealis based on Earth's atmosphere. So that's kind of fun. Any questions about the fun stuff? It's all right, you can ask me later. All right, so the compass near a wire, we saw that it depends on the amount of current in the wire, right? So when we bring that wire near the compass, it depends on the amount of current. And we saw that simply by saying, look, if I turn the current off, there's no effect. So large current gives me a big effect. No current gives me no effect. And the magnetic field of the wire turns out to be perpendicular to the wire. So let me show you that. So we'll take our tiny compass off. And what I have here is a bunch of tiny compasses surrounding a wire. So you see the little tiny arrow? No, you can't see the arrows up there yet. I have to focus it. All right. So what you'll see when this comes into focus is a bunch of tiny compasses in here. And the tiny compasses are surrounding a wire. Okay, right now the tiny compasses are orienting in, some random position, essentially. If I blow on them, they kind of change a little bit. They're feeling each other's effects, right? Since a compass is a tiny magnet itself, so they're just kind of orienting so as to, have the lowest energy with respect to their neighbors right now. But when I turn the current on, so I've got a loop of wire here. I'm going to turn the current on. Something happened, all right? So all the little magnets that were nearby lined up in a particular orientation, okay? Now I'm running the current this way in the loop, and so what's going on is that the current's going this way, and the magnetic field is curling around it this direction. That's what those little compasses show you. So in fact, this gives us a type of right-hand rule to figure out which direction the field goes. If you know the current's going this way along a wire, you point your thumb along that, take your right thumb, point your right thumb along the direction of the current, and then your fingers curl in the direction of the magnetic field. And that's what you're seeing here in the compasses, okay? And then if I want to reverse the direction, I kind of have to jiggle these guys a little bit because they get stuck. So jiggle them to randomize again. And then, yes, it did what it's supposed to do. It reversed its direction. So now the current's going up, and the magnetic field is curling around it. So when you see a wire with current in it, think along those lines. Think of pointing your right thumb along the direction of the current, and then the direction your fingers rotate around will tell you the direction of the magnetic field. So the magnetic field lines are little circles around the wire itself. Do you have any questions about that? Okay. All right, and this is the pattern that that looks like. Okay, so it's in this direction. So for current heading to the right in this diagram, put your right thumb along the current, and then the magnetic field lines curl around that. Okay, so we know now that moving charges create a magnetic field. Okay, we saw in the experiment with the little compasses what the pattern of those magnetic field lines must be. Okay, so now we're ready to see the math behind that. So here's the math that describes that. It's called the Biot-Savart Law. The key idea is that moving charges create a magnetic field, and here's the magnetic field they create. We use the vector B to represent magnetic field. So B is mu naught over 4 pi. Mu naught is just some constants to get the units right. Okay, so mu naught will make sure that when you use this equation in SI units, you get Teslas out of it. So mu naught over 4 pi times Q V cross r hat over r squared. So let me tell you what all that means. Q is the magnitude of the charge. This is for a point charge, by the way, so a single point charge. We will eventually use this equation to build up to a current in a wire, but for now we start with a point charge. So Q is the amount of the point charge. V is the velocity of the charge, and remember that's got a particular direction, so this is a vector. And that's crossed into r hat divided by r squared. Now what's r? This is actually key. So here's a diagram illustrating that. Here's a charged particle Q. It's got a particular velocity v. I want to know the magnetic field somewhere else in space. And remember what you do in this case. Imagine yourself standing at the observation point. So here's where I want to know it. There's the observation point. R points to me, right? I stand at the observation point. R points to me. So R is a vector that goes from the point charge to me at the observation point. That's R. All right? And then I need to take V cross R hat, and that will give me the magnetic field. All right? And what you'll find is that V and R define a plane, right? So if I have any two vectors, right? Doesn't matter which direction they point, but any two vectors always define a plane, right? And you'll find that the magnetic field points out of that plane every time, right? And that's due to this cross product. Okay, so here's how you know the direction of the cross product. This is the right-hand rule, okay? So the right-hand rule, and by the way, always use your right hand for the right-hand rules, okay? You lefties, you actually have the advantage in this case, because I can't tell you how many times we've been watching an exam happen. The people who are left-handed are writing the exam with their left hand because they're left-handed. And they're using the right-hand rule while they write, okay? They're doing great. I see some of you right-handed people don't let this be you. I see people writing on the exam with their right hand, trying to do the right-hand rule with their left hand. Doesn't work, okay? So if you are a right-handed person, you're going to have to put the pen down and then do the right-hand rule. I'm sorry, this puts you at a disadvantage on exams, but lefties need a break. Am I right, lefties? Yeah, okay. So lefties have the advantage here. So here's how, I just called out all the lefties in the room. Okay, so here's how you apply the right-hand rule. So you're going to have two vectors, and you need to take the cross product. I need a cross product of V cross R hat in this case. Okay? I've written V cross R because R is parallel. I just need the direction. The result of the cross product is always perpendicular to V and R. Okay? So if I need to take A cross B, for example, I'll first point my fingers along the direction of A, which in this diagram is back that way, and then leave my hand there, all right? Leave your arm there, and point your fingers in the direction of B, the second vector. Now stick your thumb out, and that's the direction of the cross product. So in this case, I had A, okay? Curl your fingers in the direction of B, cross B here. My thumb points in the direction of A cross B, right? So in this case right here of the right-hand rule for a point charge that's moving, I'm going to need V cross R hat. So I'm going to think in terms of putting my hand first along the V, the velocity, and then I need to curl my fingers along the direction of R, and then my thumb will point in the direction of the magnetic field. Do you have any questions about that? Always use your right hand for the right-hand rule, right? Okay. How do you know which hand is your right hand? Which says L? That's my left hand. Okay, all right, just making sure. Okay, any questions so far? Good. You want to know another cool trick about your hands? I got to share this with you. Because you guys, I see you. Interviews happen on campus, and I know a lot of you go off for job interviews and stuff like that, okay? Which is great. We wish you the best of luck in your job interviews. So let me tell you a good hint when you're out on a job interview dinner. Here's the other best thing about your hands, okay? Which one of these says B? Right? Which one says D? Okay? All right. All right. When you're sitting down in a restaurant, right? Your bread is on the left-hand side, and your drink is on the right-hand side. You'll never mess it up again. Okay, good. All right. See, you learn good things if you come to class, don't you? I just saved you all that embarrassment on a job interview. Good. Alternatives to the right-hand rule. This is from XKCD. Oh, some people have seen this comic already. All right, XKCD. Love that comic. All right, so you could use the book rule if you don't like the right-hand rule, okay? The book rule is you open a book in the following way. Put the front cover along the first vector A, put the back cover along the second vector B, and then the spine points towards the cross product, okay? You can also use the handgun rule, all right? I don't recommend this for real. I recommend doing this in your head, okay? So an imaginary handgun. So point the grip along the first vector, rotate it so that the safety side points towards B, and then fire the imaginary bullet. The direction of the imaginary bullet is towards the cross product, okay? So if you get bored with the right-hand rule, you can apply one of these other alternatives to the right-hand rule. So let me show you the math associated with this, okay? So in physics, we can think about physics being expressed in different languages, right? So we talk about it in English, we draw it in diagrams, sometimes we express it in math, okay? So the math associated with the right-hand rule is this. A cross B, any vectors A cross B, I can write out in determinate language. It's just kind of a shorthand for how to do this. I can write it out in determinate language. So here these big lines mean determinants. And the way I set this up is I have x hat, y hat, z hat on the top row. Then the next row is the components of the first vector, ax, ay, and az. The third row is the components of the second vector, bx, by, and bz. So here's how I take a cross product. You may have your own shorthand for it. But when I want to take the determinant of a matrix, first thing I do is copy down the first two columns. That's how I was taught to do it. So just write them down again. X hat, ax, bx, y hat, ay, by. All right? Now I'm going to set up my answer, set up the answer over here. I'm going to have some terms that are in the x hat direction, some terms in the y hat direction, and some terms in the z hat direction. Okay? And the key is that for the terms that head down and to the right, so now I draw some arrows down and right diagonally, right? Whatever this arrow picks up gets a plus sign and goes in the x hat direction. So that's ay times bz in the x hat direction. That term goes here. Okay? This green arrow picks up y hat, az, and bx. So I need to take az times bx in the y hat direction, and it comes up with a plus sign. This one right here, same thing. I pick up whatever comes along the arrow. Z hat times ax times by. That all goes here in the z hat direction. Okay? And then the minus sign terms go the other direction. I draw diagonally up arrows to the right, and whatever that hits gets put over here with a minus sign. So I'll have bx times ay times z hat. That term goes right here with a minus sign, minus ay bx. And I just fill that out, and that's how mathematically you take the cross product. Okay? Do you have any questions about that? I mean, basically, once you write down the determinant, you can use whatever trick you like for taking the determinant. Okay? Any questions about how that goes? All right, so now you have two ways to do it, but I recommend doing both ways, right? Use the right-hand rule to figure out which way it should point, then do the math, and let them check each other, okay? Let your math and your right-hand rule double check each other, all right? And the resulting vector ultimately has this magnitude. A cross B, the magnitude of it will be the magnitude of A times the magnitude of B times sine theta. So here, if A was this direction, B was this direction, there's an angle theta between them. Then you take sine of theta to give you sine of theta times magnitude of A times magnitude of B gives you the total magnitude of A cross B. Right? Any questions about that part? Okay, that's what we did today. I'll see you guys at the extended helpathon tomorrow and then at the exam. Study hard and do well, because when you study hard and do well, that was weird. I did not do that.